We can't just fly off easily into space. And sadly, we aren't able to see outer space with human eyes easily. However, using the telescope would solve this problem. Optical systems such as cameras, microscopes, and telescopes have these three variables. The first is the aperture, which is the main lens or the main mirror that gathers the light on a focus. Second is the focal length. It is the distance from the focus point. The objective is basically a device that collects light, so the bigger the objective, the more light it collects. Think of it as a giant bucket on a very lightly sprinkling day. Even if it was only raining a tiny bit, if the bucket was wide enough, it will collect enough water. Unfortunately, our eye's objective is less than a centimeter long. However, the telescope's objective is very, very big. It is essentially a device with a large objective that provides more light to your eye, like a funnel. Light has several actions. This includes refraction, reflection, and also transmission. The first two actions, reflection and refraction, are used in telescopes. They are called refracting and reflecting telescopes. When the eye looks through a refracting telescope, the light that hits the eye goes through two lenses. The first is the objective lens, which is convex, and the eyepiece lens is the concave lens. The objective lens refracts the light and it focuses it onto the eyepiece lens. Then the eyepiece lens refracts the light back to a parallel for the eye to see. However, because light has different frequencies such as red light, blue light, and green light, the different frequencies tend to bend at slightly different angles. Because of this, it is hard to see exact images in perfectly focused colors. It is also very hard to set it up for a sophisticated research. This is why Newton came up with the reflecting telescope. When the eye looks through a reflecting telescope, it is looking at light that bounced off two mirrors and then went through a small convex lens. The light first reflects off of the primary mirror, which then bounces all the frequencies and light together off to the secondary mirror. It then reflects the non-parallel light into the convex lens that matches the light back into parallel for the eye to recognize the image properly on the retina. Also, this telescope is much easier to use in a sophisticated setting because the primary mirror, the objective, can be supported by a stronger structure because mirrors only require one side to be used, so it doesn't have to be suspended like a lens. Also, because the mirror can be made thick throughout, it doesn't have the risk of thin ends breaking off like a lens does. When the objective is bigger, the more light is collected, so we can essentially see farther away things easier. When only visual light is used in a telescope, there is not much information, and more is needed for sophisticated research, which a scientist would probably want. Simply by using different frequencies of light, we can get more information about the object we are looking at from outer space. However, when using waves such as radio waves, the wavelengths are way too long for us to use a normal telescope, and also the human eye won't be able to decipher what is coming through. So we use something called a metal disc. When the light bounces off the parabolic dish, it goes to the receiver. And the receiver is connected to an amplifier and a computer. The information that is received from the receiver goes through the amplifier and goes in the computer, which then deciphers the image for us. Now we can look at things such as the Milky Way in different perspectives of light. Now we can see objects such as the Milky Way in gamma ray, X-ray, radio wave, microwave, near infrared, and far infrared. Finally, by combining all these images together, we can get the final sophisticated product of the Milky Way as you can see on the screen. And now we are able to solve many mysteries about outer space by using reflecting and refracting.